I want to talk about intentionality. And intentionality to me means how do we express what the data actually represents? Here's something that has been occupying me for the last couple of days. When we talk about intentionality, we're talking about how do we model what actually happened in the real world? And here's something to consider. It is very, very rare in the Python standard library or in major third-party tools to see cases where two entities, two functions, two classes, whatever the case may be, are mechanically identical but semantically distinct. What I mean is, if you were writing a library and you had two functions, f and g, and they both did the same thing. Mechanically, they take the same inputs and they give the same output subject to the same computation. Why on earth are there two of them? An argument might be there may be a circumstance where they mean different things to a human being even though they mechanically do the same thing. This may be apply adjustment, and this may be rebate customer. And you can think that the choice of these is your modeling of what actually happened, the intention of what somebody was trying to do in the real world, even though the mechanics are the same. Now, one thing to consider whenever you're considering how we model things, especially how we model things with functions, is update anomalies. And one of the ideas behind update anomalies is we often want to unify two blocks of code in order to create one single source of truth. Here, our choice for not unifying these and not having one single source of truth is these two represent distinct things. Today, it may be that applying an adjustment to somebody's account and rebating a customer may be mechanically identical. But tomorrow, we might say, oh, you know what, when we rebate, we have to apply a 90% discount on this. There's a 10% restocking fee. And it may be how these diverge over time that gives us the reasoning for why we might have mechanically identical but semantically distinct entities. Let me show you another example. Let's say we have a classic stock trading example. We have some desire to model trades, buys and sells of some assets, and we want to do some reporting on them. We want to report what the positions are. We want to report how much you have of each one of these assets. And you can see here we model this as a buy class representing the buy and a sell class representing the sell, a trades here, and we've used a default dictionary to compute our positions. Well, when we think deeply about how this code should be modeled, is it really the case that we need to have a buy class and a sell class? When you look at them, they're actually quite similar. The quantity is just negative in one case and positive in the other case. So maybe it's the case where, rightfully, we want to unify these into a trade class, a class that represents a trade. And the buy or the sell is just the direction of the trade, positive if you bought something, negative if you sold something. But it is very common in these scenarios, especially when you're working in the fixed income sphere, that bonds will pay in kind, or that mistakes made along the way require adjustments, or that stocks, that equity will split, or for whatever consequence, you may have some sort of additional pay in kind disbursement to you. And so, even though you've unified the buy and the sell, you may want to disunify the delta, the idea of the trade being something that you affirmatively went out and performed a trade, from an adjustment. It is very common in actual financial systems, the ones that I've worked on, that people did not make this distinction. So every time somebody had to go in and adjust an account, the product controllers had to make an adjustment here or an adjustment there to account for something weird that happened in the market, something weird that happened with a counterparty or with some settlement, in some settlement process. They modeled it as a phony trade. And they stored somewhere in the metadata, phony trade, not actual trade with real counterparty. But the problem is, because it looked almost indistinguishable from a real trade, when you start computing interesting things like average buy price or average sell price, you no longer have the ability to distinguish these anymore. And so suddenly people have to come up with these very complex mechanics to reconstitute something that was visible when, and that was known when the data was first created, when the entry was first added. Fundamentally, when you're thinking about how you model your data, consider at what point in time you have all of the information to capture what is the intention of what somebody was trying to do, and do not lose track of that. Modeling these, even though they are mechanically identical, the code is identical, distinguishing between the two of these is something which has very high likelihood to be an aspect that somebody's going to come to you later on and say, oh, you know what? Can you give me the average buy price, but don't include adjustments because we don't include adjustments in the average buy price. We only care about the trades you actually performed. And if you lost track of the human intentionality, that's no good. And you might say, well, why don't we just model everything as a delta? That's fine, as long as you track somewhere what was the actual physical human decision that led to this, what was the underlying intention. Here's something that you can think gets very complicated. When you perform trades, those trades are sometimes rolled back. When you perform trades, it's sometimes the case that the counterparty decays them. I don't know about this trade. I can't process it. There was a mistake on our end. I thought it was for 1 million, and you thought it was for 100,000. One thing that's missing from even this modeling is maybe what we want to store in this data is not whether it was a trade or an adjustment, but whether it was an attempted trade. And adjustments are more or less they always succeed. I think it's difficult for us to come up with a circumstance where the adjustment doesn't succeed. And maybe what we really need to do is we need to model what the person actually did. They attempted to enter a trade. Compute from that what the actual inferred trades are, assuming under a simple heuristic that unless somebody tells you otherwise, an attempted trade is a successful trade. Track the provenance of the successful trade back to the attempted trade, and then, at the reporting layer, actually reduce these down to what the positions are, such that later on when somebody says, oh, these 3 trades that were attempted, well, the market came back to us, the exchange came back to us and said, you know what, they're actually rolling all of these back because one of their major contributors, one of the major parties doesn't want these to go through, otherwise they'll go bankrupt. And all of these attempted trades that you, under your heuristic, assume would go through, well, we actually need to be able to tease those apart and mark that those didn't go through. And if you lose intentionality, you will almost certainly either have to reconstitute it later, try and figure out from what it is that you captured. Oh, this was done exactly at midnight. Okay, that probably wasn't a trader acting, so any trades we see at midnight are probably inferred to be phony trades or rollbacks or whatever. No. You already had that information, you threw it away. Preserve that information, preserve the intentionality of what a human being actually did or what actually triggered this action, ideally with the provenance between what was intended to happen and what you devolve this down to for easy analytical use cases, and you will reduce the churn in your code.